Welcome to the next lecture of information theory. Unfortunately, in last lecture, I have used a concept of relative entropy without defining that. That was because one of my videos got corrupted at the end. I had actually a lecture before that in which I explained it, but the software which I was using, that itself got corrupted, and somehow after recording for half an hour, I lost the file. Then I directly uploaded another video. Now I am dedicating this particular video only for relative entropy, so you can now watch this video completely first. Then you will be very much comfortable with the last lecture, where we used the concept of relative entropy to prove some inequality for entropy. Now here is the concept of relative entropy. So now here is a scenario as an example. Suppose you have a coin, okay, say it is a biased coin. So biased coin means that probability of head, which you may also call probability that some random variable s is equal to 0, that is some p, and probability of tail, which you can call as probability s is equal to 1, that can be suppose 1 minus p. And you are the owner of this coin, and you have fabricated, or you can say manipulated, this coin in such a way you know the exact value of p. Suppose you have calibrated the coin in such a way that p is equal to 1 by 4. So probability of head is 1 by 4 and probability of tail is 3 by 4 as an example. Sorry. Now here is another person, your friend or so. You tell him to guess the probability of head and tail. You give him the same coin and you tell him that you guess the probability. So there are several ways. In fact, there's only one way, one prominent way by which he can guess. What he can do is, that is a usual sampling procedure in statistics. He will toss this coin, suppose 100 times, okay, and he will count heads, how many heads are there, and he will count how many tails are there, and divide by 100. This will be the empirical probability of head and tail, okay. So whatever he guesses, and he comes with a conclusion that probability of head, which is also probability that s is equal to 0, is suppose some q, and probability of tail, which is probability of s is equal to 1, is 1 minus q. Now after this guess, you want to know how good this guess, quotes good, this guess is. In other words, you may like to frame it like that: how close the probability mass function q is to the probability mass function p, right? So in some sense, you need a notion of distance between two probability distributions, here probability mass functions. And suppose, let me call this distance as, let's call it d, and here's a notation for this distance. So d between p, and I then put a double bar and q. So I will retain this notion. So you can also think of this as suppose some d p comma q, nothing wrong, okay. Distance between, not exact distance, in some sense some distance, some gap between p and q. And what should be its property? When p is exactly equal to q, that is, your guess is perfect. Actually, we should write q is equal to p. Then this distance should be 0. That is one thing. Also, if your Q is 0 for any case, and your P is not 0, P is strictly some non-zero, then you are too much deviating, right? The probability is non-zero and you are claiming it is 0. You are too much deviating. Then this distance, in that case, it should tend to some infinity. It should diverge a lot. Now one of the ways is, suppose in case of this, again, coin tossing. So if you write P divided by Q and you put a log on it, so this is one of the functions which satisfy this property. You can see clearly that if Q is equal to P, it becomes log of 1, and that is 0, right? And also if Q tends to 0, then this log of P over Q, it goes to actually minus, it goes to infinity, plus infinity, right? Because P by Q goes to infinity, so it diverges. Now this is the sort of a divergence, we can call it, between two distributions, P and Q. Now since we believe that P is the actual distribution, P is our actual hypothesis about the distribution, so this is not the only possible case. The other possible case is, suppose if there is a tail, then in that case the divergence is log of 1 minus P divided by log of 1 minus Q, right? This was for head, this was for tail. Now what is the average divergence or average distance? So that will be, if head is occurred, so P times log of P by Q, or if tail has occurred, 1 minus P times 1 minus P times log of 1 minus P divided by 1 minus Q. Okay, now this quantity is called relative entropy. Also, relative entropy between two distributions P and Q. And notation is like this: P log to the base 2 P over Q plus 1 minus P log to the base 2 1 minus P divided by 1 minus Q. Now we can generalize its definition. So here it was defined for any binary case. So you can say we defined relative entropy for any Bernoulli event. Okay, so coin tossing is one of the realization of Bernoulli event. Okay, so S was Bernoulli random variable. It can take only two values. Now suppose you have a general alphabet set S as usual, so, and it can take any values, S0, S1, Sk minus 1, and we have two probability distributions over it, and since it is a discrete case of probability mass functions, we have two probability mass functions. So one will be denoted by, suppose, P0, P1 to Pk minus 1, where this Pk is probability, the random variable S takes some value small sk. In case of coin tossing, you can again compare. K was there 2, S0 was 0, S1 was 1, so on and so forth. So you can compare it with that. Or if you have a die, then K is equal to 6, and you have S0 is equal to 1 up to S5 is equal to 6, right? So you can compare it with that. Now there is another probability distribution, another PMF, that will be, suppose, Q0, Q1, Qk minus 1. So what it can be, suppose P0, P1 up to Pk minus 1 is a true distribution, Q0, Q1 up to Qk minus 1, that is the guess, suppose. Now you want to know how close they are, how good is the guess. Again, so you will take log as usual, suppose Pk over Qk, right? Now what is the expected value of this? That will be Pk times this and summation k is equal to 0 to k minus 1. This is the expected divergence or expected distance between the two distributions, and this is what is called relative entropy. Notation is P first distribution, then double that parallel lines, then Q. This is called relative entropy. Or it has a special name in honor of two famous statisticians. One is Kullback Leibler. They were the two who actually introduced this notion. It's called Kullback Leibler divergence, also called KL divergence. You see, in this discussion, is there anything about communication? No. It is a general probabilistic thing, and here is the power of KL divergence. It's very useful in not only in communication systems, it has a lot of applications these days in machine learning. Okay, I don't know if there are several computer science graduates in our course, and they definitely would have done logistic regression, and if you look in that sense, KL divergence looks like your cross entropy. Okay, so use that as a cost function there in logistic regression. And let me tell you here one point, that in machine learning there are several divergences. You can define distance between or closeness between two distributions in several ways. There are thousands of ways. So this is one of the way, and a simplest way, I can say that the simplest way to define divergence or gap between two distributions, and it has quite good intuition also. But there are other ways also. But in this course, we will need this much only. Now I need to actually, here is one small, I should say, lemma. The lemma is that the divergence between two distributions is always non-negative. It cannot be negative. Okay, it is always either equal to 0 or greater than 0. In fact, we know that it is equal to 0 if and only if P is equal to Q, right? That is, Pk is equal to Qk for all k is equal to 1 to k minus 1. That we know, right? Now we need to prove actually it is greater than 0, greater than or equal to 0. Anyways, now to prove it, I need a small inequality. So that inequality has very simple intuition. In fact, you can prove this inequality from a very simple calculus based arguments. So here is that. So suppose if you plot log of x, just a moment, let me plot log of x like this. Okay, so this is log of x to the base e. Okay, and the other thing you plot is so here is x is equal to 1, so this is y is equal to x minus 1. I may not be accurate, and here is 1. So what we find is that log of x to the base e is lies always below the line x minus 1, and in fact at x is equal to 1 they have the same value, otherwise it lies below it. So we can easily write one inequality which will be useful for us, that is log of x to the base e is less than or equal to x minus 1. Okay, and suppose if you have log of x with respect to some other base b, then you can convert it. So that will be log of x to the base e divided by log of b to the base e. You should remember this. And now log of x is less than or equal to 1, so this is less than or equal to 1 over log of b to the base e times x minus 1. Okay, now in particular, if b is 2 as we are taking, so log of x to the base 2 is log of x to the base e divided by log of 2 to the base e, which is less than or equal to 1 over log of 2 to the base e x minus 1. Okay, now we will use this inequality, step by step. Now first thing is we will start now the proof of lemma. Okay, now here it goes. D of p q is defined as so it is here pk log of pk by qk, correct. I will do one thing, I will reverse the log of pk by qk, so you know that so you should know this basic fact. So log of x by y is minus log of y by x. Okay, so it will be minus pk log of qk by pk, right. Now look at this. So now log of qk over pk, if you take this as x, it is base 2. Okay, so you can write it as log of 2 to the base x. Then you know that it is equal to log of e to the base x to the base e log of 2 to the base e, and this is less than or equal to 1 over log 2 x minus 1, which is 1 over log 2 x is qk over pk minus 1, right. Now this is about so log of qk by pk, so minus log of qk by pk to the base 2 will be greater than or equal to 1 over log 2 qk by pk minus 1. Right, so hence we can write d of p q is greater than or equal to 1 over log 2 base e k is equal to 1 to k minus 1 pk qk by pk minus 1, right. I have just used this inequality here, and I can now write 1 over log 2 to the base e summation. Now pk gets cancelled, so it's qk minus pk. So this is 1 over log base to the base e log 2 to the base e okay. Now see, qk and pk both are probability mass functions, so they should sum up to 1, right. Summation of any probability distribution should be equal to 1 over all the values. Similarly, summation pk should be 1. So this is simply 1 over log 2 to the base e 1 minus 1, which is 0. So it means that the relative divergence, relative entropy or divergence is non-negative. Okay, and if you see equality, when is equality attained, that we can see from this plot also. So log of x is equal to log x minus 1 when x is equal to 1. Okay, since we have put here x as qk by pk, so it means that relative entropy is equal to 0 when p is exactly same as q, p is equal to q, right. So this is the proof of the theorem, and this is one of the properties of relative entropy. Now you can easily get what we studied in previous lecture. So you should now again watch that previous lecture and you will now understand it properly.